I'm Jake O'Neill, creator of Animagraphs, and over the last couple of months, I researched, scripted, 3D modeled, animated, and scored this project. This is how Hoover Dam works. The dam has undergone many changes since its construction, so I've chosen to feature things as they appear in the original design documents. Construction began in 1931, and the facility officially opened in 1936, well ahead of schedule. The goals of the project were aligned with what dams naturally do. That is, to control flooding, sediment deposit, store water for irrigation and municipal use, and generally make a downstream river that's predictable and tame, which the Colorado River was not. After these main goals comes electricity generation, whose income eventually repaid the entire cost of the dam in full as of 1987, some 51 years after the dam's power plant was put into operation. It provides irrigation water for 2 million acres, municipal water for urban centers like Los Angeles, Phoenix, Tucson, and Las Vegas, and enough hydroelectric power for 1.3 million people every year. Hoover Dam is the site of many firsts, since nothing of this size had been attempted before. The project used around 4,400,000 cubic yards of concrete, of which about 2/3, or 3,250,000 cubic yards, went into the dam itself. The amount of concrete in the dam alone is enough to completely fill roughly 5,850 average-sized U.S. homes with concrete. From foundation to crest, it measures 727 feet high. It's about 666 feet thick at its base, tapering to around 50 feet wide at the top. The design is called an arch gravity dam because it combines two designs into one structure. The simpler straight gravity dam uses a tapered shape where the mass of material in the dam is used to counteract the weight of water pressing upon it. An arch dam uses less material, but requires strong support at arch ends. The site selection and design of Hoover Dam make the arch gravity form ideal. Black Canyon's sheer, solid rock walls provide ample arch support, while the wide base of the dam takes advantage of the simpler gravity dam design for added strength. The resulting reservoir behind the dam represents about 2 years' worth of normal river flow in storage, with a total capacity of about 9.2 trillion gallons of water. This is Lake Mead, the largest reservoir in the United States. Intake towers in the reservoir at the upstream face of the dam take in water, which flows through pipes to turbines for electricity generation. Before it rejoins the river flow below. There are other outlets, such as the valve houses built into canyon walls for water which is not used to generate electricity. Spillways high up at canyon sides but below the crest height of the dam provide emergency flood protection, with outlet gates further down the river channel. With this general picture of the project in mind, let's return to the site of Hoover Dam in Black Canyon. In the design documents, I found detailed mappings of canyon walls at various points, so I was able to rebuild the basic canyon shape as it existed before any rock was removed. The amount of concrete used in the dam is nearly doubled by the amount of excavation of all types required to build it, from rock blasting to mud and muck removal, totaling around 6 million cubic yards of material. Here's what the excavation imprint looks like at completion. We'll get into all these excavations as we go through each part of the project. The first task engineers face is to divert the entire river flow and remove all water from the dam build site. A few key structures were built for this purpose, the first of which are 4 massive water diversion tunnels. They average nearly 4,000 feet long apiece, or 3/4 of a mile, and are 56 feet in diameter. To split up the enormous undertaking, special access passages called adits are excavated first, about midway between diversion tunnel openings, at what would be the downstream face of the dam's foundation. In mining terms, a tunnel generally passes all the way through, while an adit is open at only one end and might connect to a tunnel. Let's head down to the adit opening at the Nevada side of the canyon. Some of the first blast holes were drilled from boats or barges on the river itself, before a shelf of rubble was formed to work from. This is an air-powered, diamond-tipped drill, also called a drifter drill. The tip, or bit, has inlaid diamonds called bort, which are darker, non-gem quality, imperfectly formed stones that serve various industrial uses. This bit can last through several thousand feet of rock drilling before needing service. Among bit types used are plug bits, as shown, and core bits. Designed to leave a cylinder of material at the center, for example, to take long samples of rock at various depths for inspection. Drill steel can be added as drilling progresses for boring hundreds of feet deep. The drill would have a nearby air compressor and water for lubrication. Holes are placed a couple feet apart and dynamite inserted to blast away the rock. These adits are 10 feet wide by 8 feet tall, averaging 700 feet in length, and took around 3 months to complete. Having reached the intersection with diversion tunnels, 12 by 12 foot tunnel headings are opened here at the midpoint. And at tunnel ends. From here on out, work progresses from all of these sites at once until they meet. Let's have a look at how drilling and excavation proceeds as we head to an upstream tunnel opening on the Nevada side. We see the 12 by 12 foot central heading opened into the rock. Rock drills can be mounted to a metal pipe or brace for stability. In this case, multiple braces and drills. There would be an operator at each drill for faster progress. My model shows huge stacked slabs beneath that, inside of the intended 56 foot diameter final tunnel size. These correspond to drilling and excavation sections. They're about 15 feet high, drilled to a max roughly 23 foot deep. For these sections, a special mobile drilling rig was built on the back of a heavy truck. It can hold many drills on 3 separate levels. I've shown 18 drills attached to the rig here. The top 2 drill rows handle the upper and middle bench, while the bottom drills take on the lower portion in successive rounds of drilling for between 26 to 30 holes in all. A raised flat section is left in the middle of the tunnel to act as a construction road. The top heading progresses 1 round of drilling ahead of the main section. Heading drills also handle smaller wing sections at either side. The heading wings and main benches are blasted at the same time. To remove resulting rubble, 100-ton electric shovels are used, and trucks. Some of these were specially made trucks that had much more horsepower, twice the carrying capacity at 16 cubic yards, and weighed much less than other heavy trucks of the period, with frames made of special lightweight aluminum alloys. Excavation started with headings in June 1931. The complete tunnel excavation, minus the elevated road part in the middle, finished in April 1932, nearly a year later, with an average advancement of about 73 feet per day. The raised road in the middle was also then removed, which took another 3 months. It's a total excavation of some 15,900 plus feet, or about 3 miles of tunneling at 56 feet across. Staggering. After excavation, the tunnels are lined with concrete at an average 3-foot wall thickness throughout for added durability and smooth water flow within. The lowest section is lined first. A rolling crane called a gantry rides on curbs poured at either side. Trucks bring in concrete, for example in 2-yard capacity hopper buckets. Which are lifted up over metal forms. Once poured, the concrete is smoothed into shape with a screed plate, in this case a metal arched beam that slides along the concrete forms. Next, the sidewalls are lined with a rolling rig called the sidewall jumbo. Metal arched side plates have chutes and openings for pouring concrete. Which is lifted into position from a metal crane. And finally, we see the arch jumbo rig for placing concrete in the overhead section of the tunnel. Since concrete can't simply be poured out in this case, it's pumped through delivery hoses with a following rig and machinery. With concrete placed, the 56-foot tunnel bore is now a 50-foot interior diameter lined tunnel. To seal and strengthen the installation, grout is injected through the concrete into surrounding rock. Holes are drilled at intervals and depths from 24 to 50 feet deep and more, depending on location and desired outcome. Large rolling rigs, like those used for concrete, carry machinery through the tunnel to pump grout at closely monitored pressure targets into these holes. Extra grout is needed above the tunnel where concrete has settled more. Grout bears similarities to concrete. It's essentially a mix of powder elements, or cement, and water that cures solid. With concrete, larger particles or aggregates are added to cement, like gravel, stones, or rocks. Grout generally has a much finer and possibly more liquid consistency overall, allowing it to be pumped into and properly fill cavities, both between concrete and stone and into the rock mass itself. Thus, the natural crevices, fault lines, and cracks are filled solid, down to the smallest of cavities at fractions of inches. The tunnel is bound and sealed with the surrounding rock to form one monolithic structure. Numerous drill cores are taken to inspect the rock and grout, ensuring proper grout penetration, curing, and so on through the desired depth. We're going to see a lot more of this process as the project progresses, combining concrete and pressurized grout injection to essentially weld the dam installation into the rock, forming one massive unified structure. The tunnels are intentionally overbuilt to handle the worst recorded flood conditions. Throughout the project, river flows remained ideal, such that only 3 tunnels were ever in use at the same time, and often only 1 or 2 tunnels handled all river bypass flow. With diversion tunnels completed, the site dewatering process can begin. Small temporary dams at tunnel entrances are removed, allowing water to flow through. Rock and rubble piles are dumped into the river and water is pumped out, exposing the riverbed. These rubble piles are not sufficient nor intended to properly protect the worksite through to dam completion on their own. For this purpose, fortified cofferdams are built, both upstream and down. The upstream cofferdam is the more involved of these, since it has to hold the entire river back throughout dam construction, protecting the lives of thousands of workers, pieces of equipment, and the in-progress dam itself. Among other detailed preparations, larger rock aggregates are laid first, then finer gravel and sand. The face is lined with a thick layer of concrete. The smaller downstream cofferdam is built in a similar way, but not lined with concrete. When the project was completed, the upstream cofferdam was actually left in place. However, the downstream cofferdam was removed to allow unhindered water flow from the power plant, as we'll see later. With the cofferdams in place, riverbed excavation for the main dam can begin. The exposed riverbed was found to consist of between 20 to 30 feet of finer silt and sand, laying over deposits of gravel, boulders, and so on, increasing in size near bedrock. Excavation revealed level benches at the sides at around 600 feet elevation above sea level, and a narrower inner gorge carved into the bedrock from 600 feet down to 513 feet elevation. All material is removed to expose the solid canyon bedrock beneath. You'll remember the arch gravity design of our dam. As the dam gains elevation, it relies even more on the arch shape for strength. As such, canyon walls need to be properly prepared to receive and support the arch. Areas where the sides of the dam interface with rock are called abutments. Rock is excavated such that the angled surface complements the arch trajectory as it contacts canyon walls for the strongest possible result, to resist shearing or side-to-side movement and other destructive forces. As you can see, these abutments require no small amount of excavation work and extend from the towering canyon rim down to the river bottom below. Workers start the process perched high upon canyon walls. These are the high scalers, and they sit roped into a wooden seat called a bosun's chair, originally conceived for sailors to lower over the sides of tall ships for cleaning. There are steel anchor pins high above, with ropes for the high scaler, and an equipment tether. The high scaler uses an air-powered jackhammer to strip and clean canyon walls of loose rock as needed. Rock drills were also used to make holes from depths of 5 to 20 feet or more in preparation for huge blasting operations. Abutment work began about 3 months before the river was diverted from its channel. The exploding rock was a spectacular sight, as it was allowed to tumble into the river below. Abutment excavation took nearly a year to complete and was finished just before the first concrete was placed into the dam. With the foundation profile of the dam excavated and prepared, the foundation is ready for some preparatory grouting work. As we saw with diversion tunnels, grout is injected under pressure into existing rock formations. Keep in mind the amount of water that will be pressing against this dam at all times. Water is, if it can be said, extremely good at finding its way into every little crevice where it can flow or pass through. If water is allowed to creep through surrounding rock or the underlying foundation, over time it can cause the whole dam to shift or float upwards. Entire dams have succumbed to uplift, causing catastrophic failure, rupture, and massive flooding. This foundational guard against water seepage and resulting uplift is called the grout curtain, and its integrity is essential to the durability of the final dam. 3 rows of shallower supporting grout holes are drilled and pressure grouted along the entire foundation imprint span, from canyon rim to rim, before any concrete is laid. There will be 2 more rows of critical grout injection sites. A supporting row at the upstream lip, angled downstream, and the main grout curtain itself with the most and deepest holes, which aligns more closely to the central arch line of the dam when viewed from above. These rows will not be grouted until dam concrete has progressed above them, and then they'll be filled as the dam progresses upwards. This is to ensure all these parts shift and cure together. With all of these preparations in place, we can look towards laying concrete for the actual dam. As stated previously, the amount of concrete to be placed is absolutely astronomical. Let's have a look at some of the components needed to make this unprecedented undertaking possible. For the titanic amount of concrete needed, it makes sense to prepare and mix the concrete on site. Further upstream of our dam site, there's the low-level mixing plant, with a railway and cars for transporting concrete downstream. This plant supplied concrete for diversion tunnels as well. Another concrete mixing plant is located on the Nevada Canyon rim, called the high-level mixing plant. The gravel, rock, sand, and other particulate or aggregate material needed to make concrete is taken from surrounding areas. A few miles upstream and into a flatter area called Hemingway Wash, there's the aggregate classification plant. This plant sorts different material into predefined sizes and piles, again from sand to gravel and so on, in their respective storage mounds. Nearby rail lines cart materials to mixing plants in the canyon. There's also a nearby water clarification tank, used for removing particles from water, up on the side of a rise. All of these will later be underwater, in some cases hundreds of feet, when the reservoir of Lake Mead fills. Let's fly back to our Black Canyon worksite. To make some sense of further tools and equipment, I've shown a unit or block of concrete for the dam in its place at the riverbed. More on these blocks in a moment. Our human model gives a size perspective. At this point, we've got a pretty good idea how precipitous and rugged the canyon is. With this block and its dramatic locale in mind, let's continue looking at equipment that makes placing concrete in such a severe place possible. We'll head back up to the canyon rim. While there were roads and tunnels made from the rim down to the canyon floor, the work of transporting and dropping concrete at precise locations is handled from high above, with cableways that span canyon walls. The heaviest capacity cableway, which is still in operation today, is the 150-ton cableway, located across the downstream face of the dam. A hoist house behind the tower holds huge electric motors to operate the cableway. The carriage travels along its cable track, with pulleys or sheaves and separate cables to lower equipment and platforms attached to the carriage. Much of the heavy machinery we've seen up to this point was lowered into the canyon by cableway. There are historical photos of hulking trucks suspended way up in the air, with the driver seated at the wheel, dangling far above the canyon floor. To give an idea of capacity, this 150-ton lift could transport the weight equivalent of something like 70+ modern light pickup trucks in a single load, though of course the actual dimensions of such a load would be impractical. That said, the massive steel structures we've seen and will see do make use of this incredible carrying capacity. Along with this 150-ton principal cableway, there are at least 8 other temporary cableways installed, which were later removed when no longer needed. These are mobile cableways on tracks, with huge wheeled hoist houses at either side that advance together. This cableway, for example, makes a span of no less than 2,575 feet from rim to rim, and can travel over a comprehensive area that includes much of the dam, intake towers, and spillways. Remaining cableways cover other strategic construction areas like the power station, upstream cofferdam, and so on. Some are for equipment, others are passenger cableways for lowering workers into the canyon, and more. All might be operating simultaneously at any time, for a dense web of cable hoists slung high above the canyon floor, and a steady flow of workers and equipment to and from the site. To support these cableways, and because our wedge-shaped dam needs much more concrete placed at its wide foundation, there's a lifting device called a derrick. About halfway up the canyon wall, with its base at elevation 930 feet above sea level, or about 425 feet from the canyon floor. A derrick is different from a crane in that it has a tall mast structure and a moving boom that's generally a fixed length, with cables that extend from the mast to work the boom as the base rotates. This is a stiff-legged derrick, with rigid supporting legs to brace the mast. This particular derrick was removed once dam progress made it irrelevant. Now, let's head back to our single block in progress and place some concrete. This load comes from the high-level mixing plant by cableway in an 8 cubic yard bucket. The bucket is 6 feet in diameter and 8 feet deep. The swinging doors at the bottom will only release if a worker operates the latch mechanism, or by weight against the bottom doors as the bucket touches down. Doors swing open and the concrete batch dumps into a pile as workers shovel it smoothly across the desired area. Concrete forms at the sides are made of steel plates with supporting timber structures. The side forms have vertical corrugations called keyways to lock these blocks in with neighboring blocks and prevent excess movement. The front and rear forms have horizontal corrugations for the same reason. Though this particular block's upstream face is part of the dam exterior, so the custom form has a predefined slant and a smooth surface. Horizontal keyways are formed at the surface as well. The block you see here is the basic unit of construction for the rest of the dam. Let's bring in a few more of these blocks in their proper rows. The first bucket of concrete was placed on June 6, 1933. A month or so later, This is what we see on the canyon floor. Notice the wooden cylinder forms sticking out of a block. This is a section of an internal passageway inside the dam, of which there are many, called galleries, for inspection, grouting, drainage, and more. The network of internal galleries will feature more as we progress through dam construction. Returning back to our demonstration block, the forms at the sides are 5 feet tall, and concrete is poured over the area of a block in one 5-foot tall section or lift at a time. This one lift will require something like 100 of these 8-yard buckets to fill. What's even more incredible is that steady progress was made, with all blocks together rising an average 30 feet per month over the course of the build. A minimum of 72 hours must pass between lifts, and no more than 7 consecutive lifts can be placed on a block in 30 days. This is due to the time concrete requires to properly harden and cure. Our block becomes a huge interlocking vertical column as construction progresses upwards. If I advance the timeline some, you can see that circumferential joints side to side and radial joints from front to back are designed such that these columns nest together and resist and distribute pressure from the upstream reservoir side of the dam, ideally across the arched structure. There are many reasons for laying concrete in lifts and separate interlocking columns. One major consideration is how concrete behaves as it expands and contracts, with the dizzying collection of factors acting upon it, like outside temperature, moisture, reservoir water pressure, and so on. Like the horizontal lines in a sidewalk that provide a controlled place for cracking as the concrete expands and contracts, these columns allow movement throughout the dam in smaller sections to make it more flexible in a way, and therefore more resistant to catastrophic or unpredictable cracks that could threaten its integrity. Engineers learned through failure where previous huge concrete dams did crack and come apart under load. Another critical consideration for laying concrete is called heat of hydration. When cement powder is mixed with water, the resulting hardening reaction also generates heat. Heat can cause a mass to change volume or size dramatically, resulting in unwanted cracking as concrete hardens. It's one thing for a thin city sidewalk to release heat as it cures in open air. As you can begin to see, the absolutely gigantic mass of concrete forming our dam will have an equally mammoth heat of hydration problem. If not addressed, this concrete will not fully dissipate heat from the curing process for another 125 years, all the while undergoing changes in volume that will cause detrimental cracks to form. As such, an equally huge cooling system is implemented. Water pipes are installed between each 5-foot lift at the surface. And connected to a header pipe that runs down an 8-foot wide central slot, which has been intentionally left open for this purpose. A 50-foot tall section of concrete is cooled at a time, so all blocks in this cooling period carry the same setup. With cooling pipes and headers that run down the central slot. As our view rises upwards, we see something rather peculiar in the distance. Let's follow the cooling header pipes downstream. This structure, perched atop the downstream cofferdam, is a huge evaporation tower that functions in principle not unlike the radiator in a car. Water passes through the metal fins as air moves by to cool the circulating water. There's a water pump and processing plant nearby. This apparatus has air cooling and also refrigeration capabilities for added cooling effect. Water flows through the cooling system as heat is absorbed and carried out of the concrete. Once this 50-foot section is cooled, the joints are ready to be grouted. Let's isolate a single column to see the grouting setup. Grout pipes are installed at every other corrugation in every joint, with horizontal runs at the front and vertical pipes at the sides. The pipes have outlets at intervals to allow grout to flow into the joint. Concrete pouring has already progressed into the next 50-foot section, so the grouting plant, pump, and associated equipment is lowered by cableway and hand-trucked to a nearby internal gallery above. Grout pipes have access points pre-placed in the gallery wall for connecting to the grout mixer and pump. Bags of grout mix are lowered and then hand-trucked to the location. And the 50-foot cooled section of concrete is fully pressure grouted at every joint. Pre-installed copper grout stop plates at the top of the section keep grout contained between grouting lifts. With joints grouted, the 8-foot center slot is now filled with concrete and also grouted. The process of dam construction continues upward in this same sequence: pouring concrete, cooling, and grouting. The first bucket of concrete was poured on June 6, 1933, and the last joints were grouted on June 7, 1935, 2 years later. The dam is way more complex on top of the underlying formation I've shown. There are networks of internal galleries for inspection, water drainage, and grouting. For example, the abutment grouting gallery runs along the entire contact surface with canyon bedrock, from rim to rim. The grout curtain we saw earlier was inadequate at dam completion and had to be drilled even deeper after the dam officially went into operation, from way down deep in the heart of the structure, drilling straight through existing concrete into foundation rock beneath. There are elevator shafts at the top road level. Hoist columns, endless metal staircases, ladders, viewing portals that open to the outside dam face, and adits through rock for utility and other access needs. Rewinding some, as the main dam rises up from the canyon floor below, other essential structures and components are also taking shape. Let's look at these, starting with the intake towers at the upstream side of the dam. The foundations are blasted out of the rock canyon walls at around 894 feet above sea level, or about 389 feet above the riverbed floor. Let's focus on a single tower. It's made of solid concrete, poured into forms like the dam. A dense network of reinforcement bars fills the internal concrete structure to further strengthen the tall, slender tower, especially against earthquake shocks. Metal grates, called trash racks, are installed into grooves at the exterior. These grates catch any unwanted debris as water flows in. Underneath the grates, we see that the towers, surprisingly, make a mostly solid concrete barrel. There are only 2 inlets into this barrel, one at the foundation, and one about halfway up. The inside of the barrel is 32 feet in diameter. Each inlet makes a 9-foot tall opening. Normally, only one inlet will be in operation at a time. For all the intense flow calculations and studies made, this is all that's needed to properly supply downstream generators and so on. Intakes are placed to draw water at either high or low reservoir levels and avoid sediment from the bottom or gaps in flow if placed at the very surface, providing a range of steady, pre-calculated water pressure. At each intake opening, there's a cylindrical steel gate to stop the inflow of water entirely, for example, to service downstream components. Long rods with threaded ends provide a rotating screw action to close the gate, which takes about 52 minutes. Rods for the lower gate pass through upper rods. As we follow the rods upward, we arrive at the operating house in the top of the intake tower, which has a central motor and gearboxes to operate one or both gates. Below the operating house floor, there's a row of air vents open to the outside for the intake barrel. And below that, there are emergency bulkhead gates that ride in special grooves, which can be hoisted into place to close both upper and lower intakes if main cylinder gates fail. Let's follow reservoir water as it flows into the structure. The intake tube of this particular intake tower falls about 180 feet, where it intersects with diversion tunnel number 2 on the Nevada side of the canyon. According to the plan, a large section of the original river diversion tunnel is to be incorporated into the main dam's functionality. As such, a huge solid concrete plug has been poured into the diversion tunnel at this intersection to permanently seal shut the upper portion of the tunnel. The plug has 3 tapered sections to ensure its permanent location. In the last section, a portion of intake pipe is formed into the concrete as a curved elbow, which directs intake water through the diversion tunnel. Not just this diversion tunnel, but in fact all 4 diversion tunnels are to be repurposed for either intake tubes or spillway channels at both sides. All 4 will eventually be plugged in a similar way, where the last section of the plug forms a pipe transition for either intake or spillway channels. Not only were diversion tunnels intentionally overbuilt to handle the worst possible flood conditions, but the plan from the beginning was to repurpose these tunnels and plug them as the main dam reached heights where water overtopping was deemed unlikely, based on the remaining unplugged tunnel capacity. river conditions remained ideal as construction progressed. So, tunnels 2 and 3 for the intake towers were plugged first, leaving outer tunnels 1 and 4 at either side to handle river bypass duties. In time, Tunnel 1 on the Arizona side was closed by means of a massive reinforced steel bulkhead gate and its tunnel plug installed. The reservoir is now actively filling to reach the functional intake towers. During this reservoir fill time, all bypass flow is handled with Nevada Outer Tunnel Number 4. To regulate bypass, temporary channels and gates are installed in Tunnel Number 4's plug. These will all be permanently sealed shut, and the huge tunnel gate permanently lowered. As reservoir outflow assumes its proper path through intake towers. Let's return to the intake path. Flow calculations specify a 30-foot diameter intake pipe, whereas the diversion tunnel has a larger 50-foot diameter. So, a separate run of steel pipe is installed into the chamber. These pipes, which form part of the intake system for the dam's electrical generators, are called penstocks. As with other huge sections of pipe we'll see going forward, these 30-foot diameter steel sections were built in an on-site factory since they're far too large to transport from far away. They are hauled into the diversion tunnel through access adits in the canyon walls. Individual penstocks to feed generators branch off from this main pipe. The water intake path from the other Nevada side intake tower is a little different. Upon leaving the tower, the pipe flows mostly level. Individual penstocks branch off, and this is where water falls the 180 or so feet to the generators. Since the outermost diversion tunnel will be repurposed for the Nevada side spillway, a separate tunnel is excavated and lined with concrete to accept this intake tower's 30-foot diameter penstock feed pipe. The Arizona side generally mirrors this arrangement. From here, water flows into power generators nestled deep within power stations at both sides of the canyon. As we zoom in to a single generator, we see a 14-foot diameter butterfly valve, which can rotate to shut off water for this individual generator. The generator itself is a multi-story installation. It's 100 or so feet tall from top to bottom. Incoming water flows through a steel spiral case, or scroll, that gradually narrows, such that water speeds up to pass through it. At the center of this spiral case, there's a turbine wheel called the runner, with fins or vanes, which are driven by the fast-moving water stream. This turbine is rated for a mind-bending 115,000 horsepower. The horizontal flow is guided vertically downwards by the runner, and then out through a draft tube, so shaped for ideal water flow and exit conditions out of the turbine. The turbine housing is accessed through the turbine gallery. There's a staircase leading to a space above for access to the main shaft assembly. A floor above that supports the components that generate electricity. A huge rotor spins, driven through the main shaft by the runner below. Metal wire windings on the rotor complement a separate set of stationary windings surrounding the rotor. An exciter assembly at the top supplies some initial opposing current to these components. This existing current gives the spinning rotor something to push against to do work, or in other words, to generate additional electrical current. Without existing electrical fields in these components, simply spinning the rotor wouldn't do anything at all. Hoover Dam's generators and turbines have undergone numerous updates since original construction, but the general working principle remains the same. Heading to the outside front of the power station, there are transformers and lines which carry electricity up canyon walls. Over tilting towers at the rim on both sides. And eventually to various faraway destinations. The Arizona side generally mirrors the Nevada powerhouse. A central building provides administrative space, as well as control and monitoring panels for power generators and other dam facilities. At the other end of the power station platform, we see openings in the rock for more adits whose destination we'll see shortly, and a tunnel to a roadway that eventually exits the canyon. For a sense of scale, if you were to stand under the central building, but at the lowest point in the canyon at the very roots of the dam's foundation, you would still be some 165 feet underwater before reaching the power station platform. To maintain desired pressure and water flow through penstocks and generators, there are valves connected to the system downstream. These are the valve houses, one at either side, built right into the canyon rock walls, 180 feet above the river. At each side, 6 gigantic needle valves control water flow as it exits the system. At max flow, one of these valves is designed to release 15,500 plus gallons of water per second. The powerful stream, traveling in excess of freeway speeds, shoots across the 450 plus foot gap to strike the opposite canyon wall. These suspended valve houses serve only 2 intake towers. The lower penstocks terminate at what's called the Tunnel Plug Outlet Works. 12 more needle valves are situated, 6 to a side. A section of tunnel is widened here to accommodate a reinforced concrete room. Water flows out through the exit portals for original diversion tunnels 2 and 3. There are huge bulkhead gates which can be closed to completely dewater these tunnels if needed, for example for maintenance in the Tunnel Plug Outlet Works. The specific valve type shown here was eventually replaced after 60 years of service. in the late 1990s, with a different design and a 46% increase in output capacity. With all exit valves covered, let's look at the last way reservoir water can flow out of the finalized installation: the famous Hoover Dam spillways. There are spillway basins and channels at either side. Together, they have a combined water flow capacity of 400,000 cubic feet per second. That's 2,992,000 gallons, or 4.5 Olympic swimming pools of water per second. Niagara Falls during peak flow season averages only a quarter of that flow rate. The main dam highway crosses directly over the Arizona Spillway with a beautiful arch bridge for dramatic and even daunting views right down the throat of the 50-foot-plus diameter spillway tube mouth. The downward section of the tube falls nearly 600 feet in elevation from the spillway crest to a horizontal transition which is built into the tunnel plug for diversion tunnel number 4. From here, water travels another 1,600 or so feet to the tunnel outlet portal. Let's head back up to the top. The crests of these spillways are 27 feet below the top of the dam. As we focus on the Nevada Spillway, you can see the great drums built into the weir structure. There are 4 drums with a rounded triangular cross-section shape. They're 100 feet long and about 20 feet tall on a side. They sit in a containing chamber. As the reservoir experiences flood conditions and water flows over the spillway weir, there are screened portals at the weir face and valves to admit some water into the drum chamber. The watertight drums naturally float upwards, connected by a hinge at the reservoir side. Drum pitch can be manually controlled by closing inlet valves and draining the chamber. At maximum extension, the drums allow an additional 16 feet of water to be stored in the reservoir. If flood conditions persist, water can reach an additional 7 feet of depth above the top of the drums, at which point the drums will automatically lower to keep the reservoir at elevation 1,229 feet, just 3 feet below the dam crest at 1,232 feet. With drums lowered, if the water level rises up those 3 remaining feet, spillways will be at their 400,000 cubic foot per second flow capacity. Highest river flows average about half of that rate since measuring began in the mid-1800s. As the flood peak subsides, drums are designed to automatically raise to their full upward position and remain there until conditions allow them to naturally lower with the water level. While I've attempted to get across the sheer magnitude of Hoover Dam's structures and components, my research revealed so much more than I can show here. The project employed 21,000 people over the course of its construction. So many vast subcomponents being developed at the same time make the site look like a busy ant colony in historical photos. with detailed and interesting things happening from rim to canyon floor to rim. No matter where the future takes us, it will still require this kind of unification, of sharp minds and skilled labor to tackle huge problems and create not only solutions, but collective works of art like Hoover Dam.